Good morning, everyone. Thanks for joining the last day of this GPU programming with kernels course. I hope that you find it useful so far. Please, as I said, this is the last day. If you have any questions or any concerns, doubts about what we have seen so far, please let me know. I will be more than happy to answer the questions if I know the answer. If not, I'll find it for you. Okay, so today's agenda. Let me share. We'll make this separate. So the idea of today, that is the session 5, is review the previous exercises. Actually, the exercise of streams, and then we will learn a little bit about the graph API. We have the morning break. We will learn how to use more than one GPU, and I will explain that this exercise will be like homework in case that you want to play with the contents that you have learned so far. Okay, so let's start. I will share the terminal. Oops. And this at some point, yeah. So you see now my oops. Okay, so I'm here. Right, so the idea of this exercise is we are doing, if you see here, we are doing two heap mem copy. So what I want to do is to replace them, because this is a synchronous call, replace that with a heap mem copy asynchronous, and do this in two streams. So one stream will do the copy of the vector x, and the other stream will do the copy of the vector y. So I will need to open, have it, the documentation. Oops. Yeah, have too many windows open. Okay. Right. First of all, I said that we will need to create two streams. So let's declare them. For instance, here. So if I remember was, I need to check the documentation, otherwise, heap stream. So the type will be heap stream underscore t, and we will have a stream x and a stream y. Now that we have that, we will need to create the streams. So to create them, what we will do is use the function heap stream create, will be stream x remember that you need to pass the string by reference, so we will need the ampersand. And we'll do the same. Actually, here I will add a heap cert in case that there is an error. And now I will copy and paste and say string y. Okay, so now we have declared and created the streams. Right. What else we need to do? Remember to destroy or release the streams. So we go to the end. Here in release resources, we will add a heap assert. Oops. Is a heap stream destroy. I am following the documentation that is here. I will send you the link. Stream X. And now I'm copy and paste. Oops. Okay, so I have now heap string destroy X and Y. Perfect. Actually, this is a good practice. Every time that you allocate some memory or you create some object in memory, immediately write the release free destroy of that object. And in that case, you will never forget. Right. So we have this, and now next step is to replace the heap mem copy that we have here with the heap mem copy asynchronous. So the syntax is the same. We need only to add async. So we need to add this here. I notice also we'll make this a little bit bigger. Sorry. So we need to add this. Sync. And also we will need to add here the stream that we want to use. So here I will use a stream X and a stream Y. Here I'm creating, also bear in mind that by default we always have the default stream that I think is the ID is 0. For the stream X and stream Y, what I have is I will have 3 streams. In case that you don't want to have 3, you can create a secondary one and use the default one and the secondary one. But this is up to you. But now using stream X and stream Y, I will have 3 because it's I have the default one that this will be always there. And also we have a stream X and a stream Y. Okay. Also in the exercise said that to be careful that because this is an asynchronous copy, when we launch the kernel here, so we do the copy here. When we launch the kernel here, it could be the case that the memory is not there. So in that case, I will need to add a synchronization point. That will be, oops, is a heap string synchronize stream X, oops, and the stream Y. And I think that must be the exercise. So I break that. Because I was playing with that before, I already have that, but well, I can do another copy of the make file. Remember that it's in section 201. And I can do a make. And I did an execution before because the queue this morning is a little bit busy. And if we do sinf info is there. Well, now it's not that busy. I have yeah, 2 nodes are allocated and 2 are either, but yeah, this morning they were a little bit, and I have this execution, but I'm not sure if the exercise was okay or not. Well, okay, yeah, the results are yeah, it works. And also I have here if you see here, I have the traces that we will use then for the to use Perfecto. What I will need is to download these ones. Let's see if I download selected files. I will download them to desktop. And I think this is the one that we need, but we'll see. So downloading. Yeah, it's a bit slow, but well, it's doing. In the meantime, I will open. I think I have the Perfecto open here. Yeah. Actually, no. Here, let me make this a little bit bigger for you. Stop shading. Okay, so I will make maybe this a bit. Yeah. Make this a bit. It's not possible to make this. Well, hopefully the font is big enough. I don't know why it's not. Yeah, okay. Open trees file. I think must be this one. Let's see if that loads. It's JSON. Okay, this one, sorry. Okay, yeah, fine. Right, so I have this here. Interesting. Let me. Okay, yeah, now I can make this. Here. Okay, I see it here. As you can see, it has been a while since I don't use. Well, okay, I see. Yeah, I'm not sure if this is big enough, but okay. What I wanted to explain here, and actually this was highlighted yesterday at the end of the session. I mean, I was a discussion with the, I think was, yeah, with Andy, with one of you, that if you see here, this heap stream create takes a lot of time. And then the second call, I don't know if I can make this bigger. Give me a second. I'll try something. No, doesn't make much difference. Well, maybe you see that that line is 200 milliseconds. Yeah, 200 milliseconds. You see that the line is like almost the entire execution, let's say, with the heap string create. The second call is 7 milliseconds, and the first one is 201. It seems that I think also in checking here that you see that when we call a heap string create at the same time, that is the HSAQ create. So it could be that this is like the first call takes the first call of a heap. So a heap runtime, it seems that for the first call takes a lot of time to set up. I mean, a lot of time. We are talking here about 200 milliseconds. So this is when we also this is another point. Here we're playing with the toy exercises that are not normally if we run a software that takes half an hour, something like that, 200 milliseconds is nothing. What is interesting here is, yeah, that to see that the first call takes longer because I guess that the runtime needs to set up some things, and yeah, that's the second call takes less time. Yeah, so I will see if I can make this. Slice copy host. I'm just checking here that here I do a call of a heap memo, the asynchronous memory copy and another asynchronous memory copy. And I see that here these copies are done in parallel. You see the stream ID is 2, and here the stream ID is 1. Because as I said, the default ID, the default stream ID is a 0. So we have a 1 and 2. So you see that these copies are done in different streams. I will make this there is no okay, no, this is what I wanted to. Yeah, actually heapman set takes 8 milliseconds. Launch kernel is here, that takes 2 milliseconds. Key memory kernel. This is device synchronize. I wanted just to show you. So this is. So you see here the copy, one copy here, one copy here, and in I think that this one is the default. We have like 3 streams. So if maybe that is a better way, but I want the launch kernel. What is that? Fill buffer. Yeah, it's not shown here in the. Ah, well, okay. No, my kernel is here. It's a launch kernel. Okay, that my kernel is here. It's in a different. And if we see, okay, it's in the stream ID 3. You see, it's in a different stream. Here is the kernel. I mean, one thing is the launch kernel, but the execution seems that is here. And okay, so this is the exercise. Not sure if you have any questions. Remember, when you open a trace file, you need a JSON extension. Also, let me check the yeah, I was just checking. There is like a second part of the exercise that is replace the host allocations of X and Y with the heap host malloc, and then free resources with the heap let's see if we can give a try, see if we have time to do that. Share application, window, share. Actually, yeah, the syntax is similar. So if we go to the exercise, what the exercise says is here rather than doing this, what I will do is use heap host malloc the pointer that is X, and the size that is the size will be number of rows multiplied by size of double. This is similar to malloc. I think should be something like that. And this will be Y. Yes. And remember, best practice. So when I do this, oops, looks like okay, also the terminal was frozen for a little while. Remember always to release, oops, here rather than delete. I will use heap host free, I think was the syntax. Yeah, and the pointer, that will be X. And okay, so I can now save. Also, I will see I will cut the resources that's and see that the kernel takes this time. I will copy the time just in case. Do make, see if, oops, it's M row, not N, right? So I edit that. Oops. Make again. Now it works. Nice, batch submit, and see if the queue is faster now. Not sure if no, it's only a info. In theory, should be okay. There are 3 nodes that are idle. So, yeah, I don't know why this time I had to wait more time. Okay, now it's running. Should not take. Oh, see that is already 10. Good. So I can cut again the short stats. Oh well, okay. Actually, I mean, also, okay, let me explain that. I will copy this. We see that using pin memory is slightly faster, but bear in mind that I have executed this only once, and this pin memory, like for each version, I executed once, only one time. Could be the case that for some reason I get maybe because the GPU was they were like there could be like several reasons of the operating system or other factors that could make that the versions the runtime is different. To be sure that the pin version is faster, I will need to execute it at least, let's say, 3 times and compare if these 3 times is we have a similar time. The same with original version. So my advice here is don't run when you are benchmarking or when you are measuring times or efficiency, performance, etc. Don't run it only once. Do several runs and compare if the times are similar or accurate with respect to the previous version. If you see that all times are similar, yeah, go ahead and keep the improved version. But if not, because also this is not the case, but for instance, when you have some I/O, the times could vary in case that the ARCHER2 is busier, or could be several reasons. So my advice is to repeat the analysis several times and see. Actually, we can do that. And see if we get the same. Goes right. Also, what we are measuring here is the time of the kernel. So you see that the software almost takes several seconds, but the kernel is you have seen before that we have several before running the kernel, we have the memory copies, the creation, in this case, the creation of the streams. So that takes time. And when you compare, let's say, a serial code with a GPU code, some people, what they do is compare only the kernel time. Of course, if you compare the kernel time, it's very likely that will be faster. But you should also, well, here there is like a little bit of discussion, in my opinion, that maybe I'm wrong. You should also add the time that to set up, do the memory copies, etc. In order to make a fair comparison of the serial version. But well, this is in case that you see some papers that you see that they have a speed up of I don't know, 800 or like a crazy speed up. Check if they are including the setup time, let's say. Okay, should be already done. Start CSD. Oh well, okay, now it's even faster. Say 11. Okay, so yeah, as I said, do several runs and compare, and also it depends. So some people take the average, some people take the minimum, maximum, or even you can take like the, how it's called, the like the range that they plot when they create a plot. They plot like what was the minimum, the maximum, the average of the runs. You can have like a 3 runs, 5, 7. Also depends on the budget that you have to spend of computation. Okay, any questions so far after this performance discussion? Right. Next is to see graphs. That the graphs is similar to streams. Actually, are a little bit more complex, but we'll see why. Sure. See graphs. Okay. So we have seen with the streams, we have several streams, and each stream could execute a different memory transfer or several kernels. We have talked that could be useful when we have several GPUs, so we can use different streams. But also was introduced in HEAP the idea of a graph. Graph is when you have like a more algorithm of a more complex structure of memory copies, kernels, etc. You may need a graph. Actually, we'll show you with the picture is easier. Let me see if you can see. Yeah. Here we have a stream. Stream is like actually it's kind of could be a graph, but you know that there is a line here, like we execute operation A. When I say operation, could be memory copy, kernel, something that we would run on the CPU. Kernel A, operation A, then I execute operation B, then C, and then well, I finish. These arrows are the dependency. So you cannot start operation B until operation A is done. Well, on the left we have a stream. On the right we have a graph. So we have imagine that this is these are two kernels, B and C, and A is a memory transfer. So the kernel B and the kernel C needs to wait to the memory transfer to be done. So that's why we have here these dependencies. And well, once that the kernels B and C finished, we reach the end of the. So this is a type of graph that has a direction. You see the arrows, beginning and end, and there are no closed loops. This type of graphs is called DAG, that is a directed acyclic graph, because we have direction and we don't have like a closed loops. So what we will learn now is how to create a graph that you will see that this could be a little bit well complex. We'll see that there is like a lot of new syntax, let's say. First, we need to create the graph. Remember that before we have created, well, before yesterday or this morning, we have created a string, and similar with the graph, we need to create, the arguments will be the graph and the flags. And here is specified that, the flags will be 0. We don't, well, you see here the sample, declaration, and the creation. Again, every time that you create something, well, here is kind of destroy or release or free the graph. So you see here that is passed by reference with this ampersand, and here is not needed. Okay, easy. This is just to create the graph. But now we will need to populate the graph. Actually, there are two, right, there are two steps. We have created the graph, but now here we need to instantiate the graph. That this will do we'll have some overhead setting up the launch parameters, memory, etc. This will be like some work that for the heap runtime. And once that this is instantiated, we can launch the graph. We can execute the graph. Similar that we launch or execute a kernel, we can also execute a graph. That a graph will be several operations, could be memory copies, kernels, etc. We will see the nodes that we can have. And also remember that you need to go execute this. That this is like a instantiate makes it's kind of we create the graph, but also we need to create the execution of the graph. Yeah, that's that. Yeah, a bit. And again, everything that we create, we need to destroy it. So we need to use a heap graph access destroy. I was talking about graph, the node types. So we have these ones. We have kernels. We have memory operations that the heap main copy, memset, and also we can have a CPU, nothing that we need to do with the CPU function calls. This is also another way to increase concurrency, because when we have several GPUs, or when we have some like a complex algorithm with the different dependencies, we can define them using a graph. Right. Okay, this is now we will see how to define a kernel node. So I have this kernel that is called my kernel. I have these arguments that is A, X, double, and also I execute with the number of blocks and threads per block when I instantiate that. So this is defined. To define the graph, I will have a structure called heap kernel node params that has this structure has this But here set public members. Public members is the. I have the function that this will be my kernel, the parameters of the kernel that I guess that will be A and X, number of blocks, number of threads per block and number of blocks. Here I have an example. So I define here this structure that I mentioned before, and I initialize to 0. So all of the fields of, as I said before, public members of this will be 0. And the kernel argument, I will create a vector or array, and I will, by reference, I will set A and the X, that this will be the kernel argument. And now each this structure has these 4 public members here. So I initialize with the function that will be my kernel, the arguments that have been defined here, blocks and threads per block. Oops, sorry. So now I'm ready to add the kernel node to the graph. So I need to define the node, that is a K node here, kernel node, and I need to do this operation. Heap graph add kernel node, and I need to send the node to specify the graph that I'm using, my graph. Normally this is like a null 0 and the parameters. I think this is the dependency, but for this kernel, because we don't have any dependencies, probably we will. Well, yeah, let's assume that we don't have any dependencies. This is a 0. This will create a new kernel node, add the existing header, and will return a handler. So as you can see, this is a little bit more complex because we need to do a lot of setup to create just to create one node of the graph. Well, here you have the prototype definition, the syntax that the null size is the dependencies. Here is the number of dependencies, and here is the pointer of this node. So this is what is explained here. If there is no dependencies, the third and fourth is a null and 0. Well, 0, this would be like a number. This is for the kernels. What about the memory copy? So we have another structure that is called heap memory copy 3D parameters or params. And we have the public members of the structure that we have the pointer, the source pointer, the destination pointer, also the offset, in case that of this pointer we want to, we have an offset of when we do the copy, extend the dimensions of block, and the direction of the copy, if it's from host to device or device to host. And as I said, as he said in the slides, it's a little bit more complex, this thing. But well, this is what. But here, I think if we click, we have the explanation of. This is the API of. That also is useful to have a look and see what we have here. Okay, so this is an example that I am copying from host to device. Also to remember a trick that I use to remember the direction normally is host to device. So this is copied here. So imagine that you don't have this and you have a D pointer equal host pointer. So the is always in this direction. This is copied in the, okay, you don't have here anything to write, but later I mean, this could be replaced by only this part, and you imagine that you have here a equal. So this, the value of this will be copied here. It's a way to remember the order of host to device. Yeah, this is the size that you want to copy. So to do that, to do this line of code in graph for a graph, you will need to do this. Define the node and have the heap memory 3D parameters. Again, initialize to 0. The kind that will be copy host to device. The make heap extent. Well, what you want to copy. Here, this is like a 3D. 3D means that we are copying we are making a copy of like a 1D vector, but could be the case that you have a 2D or 3D vector. So in one of each these parameters, you will have like the size. But because this is 1D, I'm only using the let's say the X axis. The Y and Z is 1, 1. The offset, because I will not have any offset, it will be 0, 0, 0 for both source and destination. And for the pointer, yeah, this is a little bit funny how to define this. Yeah, it's a bit make a heap pitch. The thing is, as you will, well, you may be already aware when you code, you will not need to remember everything. Normally, I always check the documentation to see the syntax, etc. What you need to know is what you can do. So in this course, for instance, you are learning that for GPUs, I have kernels, I have pin memory, I have streams, I have graphs. So you know what is available, and then you choose what you want to use. Once that you do that, you always check the documentation, and you will not need to remember all of this. This is a bit of a nightmare to remember all of this. Yeah, this is the way to define the pointer. What is explained here that for 1D you can create a function like you have these parameters and the function could translate that into this. Actually, it's a good idea. Yeah, that will save, will make the code more readable and save you some pain copy pasting all of this. And now I add a heap graph add main copy node. If you remember before, we add a kernel node, and now we are adding a memory copy node. And you see here that we have the memory copy node, my graph, and here I have one dependency on this of the kernel node. So I'm executing the kernel node, and this memory copy node depends on this. So once that this kernel node is finished, the memory copy node will execute. So this is the way of defining the dependencies. Well, if you go to the API, you see the data structure. Well, you will see all of this. You need to use graph, heap graphs. Oh, well, actually, oh, I haven't seen that. Yeah, here you have more documentation of the. It's quite good. I mean, well, as you can see, it's quite big. The the AMD heap documentation, but it's quite. You can have a look and see here what we were talking about the streams. You see that you have two streams, but also you can have a kernel in case that you want. Well, you can also use streams and use a heap device synchronize. But well, actually, yeah, I will use. But when you have something that is more complex than this, maybe using streams is not. Well, here they said that normally is. Okay, I understand. They said that using graph is faster than because you have the host activity and the device activity. The host activity, you see the kernel launch A. Actually, we have seen that imperfect, so that we have the kernel launch, and then in the device activity, we see that the kernel A is executed. Kernel launch B, B is executed, C is executed. You see that there is like a that is what is here the kernel launch congestion. But when you have the graph, this is what they were talking. The graph launch will take some time, but then in the device activity, because in the graph launch you have specified that the kernel B is dependent on A, you have all of the dependencies, everything defined. You see that execution is faster, and you have this time of speed up. Okay, that's interesting. Using heap graphs. Well, here is explained the general flow. Create a heap graph, the execution, and then launch. And once that everything is done, free destroy the graph resources. That will be this one, the execution, and the graph. Memory management. Well, I haven't used this, but there is a way to capture from the stream, you execute a stream and you can capture the operations that the stream does into a graph, and you can save the graph and execute it in a, but yeah, this is a, well, you can have a look, but yeah, it's a bit more complex. You see that here they use a heap check, and in our documentation we use a heap assert, but I mean it's the same. Heap check must be, yeah, it's defined here to check the errors of the, and you see that here they have different kernels, A, B, C. Hopefully after this course you will be able to like read this documentation on AMD and understand. Also you can do an explicit graph creation, that this is what is explained on the and you see that allocation time, yeah, you have all of these, but you see that to create a graph, you see that the file is, yeah, it's not easy to say, it's a bit more complex. Okay, so this is what I wanted to talk about graphs. There is an exercise at the end let's see if I well, when we launch the graph, you need before ending, you need to use activity by synchronize to see that the graph has finished. But I think this is similar when you launch a kernel. You need to wait until the kernel is finished. And again, we have this exercise, this mathematical operation that you can use a graph. Again, because this is a toy example, you will not see any, well, you may see a performance improvement, but this will not be like mm, uh, quite too much. Yeah, you can always, like a key memory copy. So yeah, this will be the exercise in case that you want to play with the graph. Not sure if there are any questions. If I'll be around, so feel free to write them in the chat. We will have an hour break, and we'll start at 11. What else we need to go through? So at 11, we will talk about device management, more than one GPU, and putting it all together. Well, this will be, I will explain the exercise of and yeah, that's okay, I'll stop now, and yeah, I'll start talking again at 11. So yeah, see you at 11. Hello again. Okay, before we continue with the lessons, I would like to show you if we go, give me a moment. If we go to the ARCHER2 training page that is here, I will copy that on the chat. You will see the GPU programming with kernels, that this is the course that we are delivering. We are now in the last session. You will see also that is available the recording of yesterday here. And please, I know that everything that you do, you get a link to fill in the feedback. But I promise that this one is very short. Well, I mean, there are a lot of optional questions. Actually, I will be interested to see what do you think about this format. We are delivering this course in 5 mornings. This course previously was delivered using 3 full days with also time for exercises, etc. But this time we decided that to have the afternoons for for the exercises and keep the mornings for the theory and the resolution of the exercises. So feel free to add any comments here. The only aspect that is mandatory is the overall satisfaction. That this is just a click over one of what you think about the course. Click here in submit, and that's it. This is the only mandatory. Why I'm requesting you that, as you may know, these courses are free for UK academics or academics based in the UK, and we need to report these numbers to the funding body that is UKRI. We need to report. We need to report this feedback. If we don't report, if not enough numbers, will be a little bit tricky for us. So please, this will not take you more than, I don't know, a minute. Just clicking here, submit, and of course, if you want to give more detailed feedback, you are more than welcome, but don't feel obliged to. I will copy that in the chat, and yeah, please, it will not take you more than one minute. I understand that everything that you do today, you fly and you get a feedback form, you buy something, you get a feedback form, you get a delivery and you get a feedback form. Yeah, I mean, let's say the same thing or have the same feeling, but yeah. Okay, this is let's stop with that and let's continue with the device management when we have more than one GPU. Okay, so what happens when we have a more than available devices? Because we are using C++, you may know that the indexing starts with the 0. So if we have one device, the device ID will be 0. If we have two devices, will be 0 and 1. We have used at the beginning, if you check the exercises, we have used at the beginning, well, heap get device, that here we will get, if we have only one device, we will get 0, so the device ID will be the 0. Also, we can get a heap get device count. This is in case that you have more than one GPU available. You can always imagine that you have, I don't know, 10 kernels, and you have 2 GPUs available. So you can launch 5 kernels to one GPU, the other 5 to other GPU. Let me check if I'm forgetting something to explain. To do that, for instance, we have 10 kernels and we want to launch some of the kernels to one GPU, other kernels to other GPU. We will need to do heap set device. When we do that, we can say if we want to use the GPU, that is the ID is 1, we do heap set device 1, and then I do all of this. When I do all of heap malloc, heap main copy, kernel launch, etc., we will use the GPU whose ID is 1, the same that with the 0. So be careful with when you do all of the operations of heap, malloc, memory copy, kernels will be done on the CPU that is on the GPU that is set with the heap set device. Also is explained here the concept of peer access. You see that we have in this example here, we have 2 GPUs, GPU 0, GPU 1, and you have 2 GPU memory. The memory here belongs to the GPU 0, and the GPU 1 have a different memory here. So this will be like a, let's say, distributed. And you have also the PCI, well, it is connected with the PCI Express. It is possible, but as you can see, it will be slow, or well, slower than the getting access. The GPU 1, you can get access. Actually, no, sorry, I start again. GPU 0. If I want to get something from the GPU 0 memory, this will be fast because we have this link here. It is also possible to get something from the GPU1 memory, but you see, rather than having like a direct connection here, I need to go through the PCI Express, GPU1, and the GPU1 memory. It will be possible, and we will avoid a data transfer. Well, I mean, data transfer, let's see, of the whole array, matrix, etc. But bear in mind that you will need to go through the PCI Express, so this will be slower, this path, rather than this. This is called peer access. It could be that it's not available, but that's why we have this function here. Heap device can access peer, and the destination will be device 1 and the source device 2. Also, you can enable, disable, you have all of these functions here. And the flags parameter, yeah, set to 0. Here we have a simple exercise that is device-to-device data transfer that you can, if you have the time, you can play with these functions, and you can also measure the time that takes to get access to well, here you measure the bandwidth of using repeated copies of the array with the keep memory copy. This exercise is a little bit more complex. I will show you that in the repository you have the solution. So if you don't want to spend time, you can always take the solution and play with that and see how it works. Let me share with you this tab instead. So yeah, here's explain the exercise. And also the exercise, in case that you want to start or you want to play what the things that you have learned so far, is use the conjugate gradient method. That there are two main steps involved. The first one here is explained with more detail, and also if you can, well, this will be the algorithm, but you can find the, well, this is written in Julia, in MATLAB. This is yeah, MATLAB. I think there are versions. If you go to Google and you search a version on C++ or even in HIP or CUDA, must be written. So yeah, this is the algorithm of. So the algorithm is this has two steps. It's a matrix vector multiplication that you have already the code, and also it's a computer scalar residual that is explained here. We don't provide a solution for this exercise because there are different solutions, and if again, if you search on Google, there are plenty of ways to do that. This is more for you to, in case that you want to apply your what you have learned so far with this. Here we have the solution of the previous exercise of a graph that we can check the solution. So this will be the new. No. Okay, here it works. This will be the new part of. You see that I will make this a bit bigger, probably. You see that they define the graph execution, and I create a graph. This is the same that we use for the kernel, that the blocks, threads per block. And here I define the graph kernel node with the arguments. Here I have the parameters, and here I add the kernel node without any dependency. Here, what is in the exercise is to add another heap memory copy device to host as a dependent. So again, I define the node, the parameters, I initialize the parameters, and I use a heap graph add memory copy node. And here I define the dependency. And then I instantiate and run the graph in the default null string. That will be 0. Null is 0. Heap assert, heap graph instantiate, launch, and device synchronize. And also, when you execute that, you can see with the perfecto how this is like a. You can compare the trace using a string and the trace using this, and you could see the differences. But yeah, here you have the solution. Also, we have here the solution of the streams, but identify that yeah, they use only one stream rather than two. But well, it's a way of doing that. What else I wanted to explain about this repository? If we go to util, you see that I have a heap and memory copy bandwidth. This one, this is the code that you can use to measure bandwidth host to device. They have like a different options. And you can play with that and see the results that you get. Also, let me check. I think it's called Archer. I think this is the name. Yes, I will show you here. I will send you the link. This is the course. This rather than ARCHER2 GPU course is called ARCHER GPU course, and it's a version of the course. Actually, the previous one that used CUDA. So in case that you see that the exercises and is pretty similar, if we go here, more than one GPU, you will see that you have the syntax, but using CUDA. Rather than heap get device count, we get CUDA get device count. CUDA get device, CUDA set device. So you have here is the same version of, well, same version, is the previous version of the course, but using CUDA rather than heap, just in case that you have access to other machine. You can always yeah, have a look and I'm trying to think about other things, but yeah, I think this is what I wanted to explain today. So now you will have a time until noon for exercises, and I'll be around in case that you have any questions or you want to go through the solution of any of the exercises again, or please, let's say this time is we have now 40 minutes. this time will be for you to play with exercises, or also to to ask me any questions that you may have. Feel free to play with exercises and ask me questions. In case that you want to leave early, I'm aware that today is a Friday, so no no offense. And also before finishing, thank you so much for attending during these 5 days. And also thank you for the questions, the comments. This is always useful to see if we are in like a good track or not, or if we need to focus explaining a bit more about like one section rather than the other. Again, in the feedback, if you have any comments or things that you may think that will be useful to improve the course or to make the course longer, shorter, we always review the feedback after the course, and for the next iteration, we one of the feedback that we took into account was to have like a rather than 3 full days, like a 5 mornings. And thanks again, and I'll be here until noon in case that you have any questions or you need anything. Thanks again, and hopefully see you in future ARCHER2 courses, or also be in touch in case that you have if you work with one of the exercises during, don't know, later today, next week, you can always contact support@archer2.pc.uk. If you contact them and you say that you are an attendee of this course, the query will go to me. You can also send me a message in case that you want to bypass the service desk. This will be my email address. And okay, I give you now time to go through the exercises or go through the theory in case that you have any questions. Thanks again, and see you. I'll be here until noon, but see you around in case that.